Alright, welcome back. Our next question in this series reads, as an illustration of the principle of relativity in classical mechanics, consider the following generic collision. In inertial frame S, particle A, mass m sub A, velocity u sub A, hits particle B, mass m sub B, velocity ub. In the course of the collision, some mass rubs off from A and onto B, and we are left with particle C, who has mass m sub C, velocity u sub C, and D, mass m sub D, velocity u sub D. Assume that the momentum P equals mu, or mu, is conserved in S. A. Prove that the momentum is conserved in inertial reference frame S bar, which moves with velocity v relative to S. B. Suppose that the collision is elastic in S. Show that it's also elastic in S bar. All right, let's go on to our next. So our solution here is pretty cunning, but pretty straightforward. So conservation of momentum reads ma ua plus mb ub equals mc uc plus md ud. Again, before and after. And this happens for before the collision, after the collision. Okay, and what we're saying is that because some of A rubs off onto B, the masses are changing, so that's where we get mc and md as expressed in the question. So under Galileo's velocity addition rule, where we have v of A relative to C is equal to v of A relative to B plus v of B relative to C, we can set this up for anything that has ui, so we can kind of index this, right? So we're left with ui equal u bar I plus v. V was the speed of the reference frame shifting, and ui was the speed in that reference frame. So ui is what we're looking at as an observer. So with that being said, if we substitute this in for A, I equal A, we get u bar A plus v, and then we do this for all the other ones. So you see we get two velocity terms and the momentum conservation law. So what we can do is distribute the masses into both those velocity terms, and then we can factor out the v's on both of them. So we have ma plus mb times v, and then mc plus md times v, which is what we didn't have before in the conservation equation. Okay, so what we can say that is, assuming that mass is conserved, i.e. ma plus mb equals mc plus md, it then follows that if that's the case, we could plug in this and cancel the MAB term on the left with the MD term on the right, and thus we recover the conservation equation, except now with the velocity in the bar system, or the prime system, whatever the textbook wants to use. So what we can say is that the momentum is actually conserved in S bar. That's pretty nifty. Now, for the second part of this question, we were told that we had an elastic collision, and we want to show that things are conserved there. Now, if we recall, in elastic collisions, we also had kinetic energy conserved. And so what we're going to have to do is the same trick, just with the kinetic energy formulas. So here we have kinetic energy of A, kinetic energy of B, and then, of course, it's conserved, so it has to equal kinetic energy C and kinetic energy D. Let's recall that when you see a velocity squared, since velocity is a vector, the square is actually representative of a dot product. And that's how we get these two, the cross term for 2, ua dot v. And we see that dot product in all of these. So by similar methods, go ahead and distribute, and then collect the v terms, the dot product of v's with the masses, and then collect the mass terms with v's as well. Basically, get all the velocity with u's on one side and all the velocities with v on the other. And do that for both sides of the equation. Okay, now what we just showed is that momentum is actually conserved in the S bar system. So if that's the case, this quantity in the big parentheses is equal to this quantity in this parentheses, and they cancel on both sides. Wonderful. What we also stated in the last slide was that mass was conserved, so MA and MB are equal to MC plus MD. So these two terms cancel. So the last two terms in the energy equation cancel out due to the conservations that we proved. So what we can say formally is by conservation of momentum, the third terms are equal and thus cancel. And the conservation of mass tells us that the last terms are equal and thus cancel. So we're left with just the kinetic energy in the U-bar, kinetic energy of B with U-bar, and C U-bar, D U-bar, and thus kinetic energy is conserved, and we are done with this problem.